Welcome and study with Tanzania Institute of Education.
We're going to look into the properties of rational numbers and irrational numbers in this lesson, but first, a recap. Natural numbers are 1, 2, 3, 4, 5, and so on. Whole numbers are the natural numbers together with 0. Integers consist of the natural numbers 0 and the negative numbers. Rational numbers are those numbers which can be expressed as a ratio or fraction between two integers. For example, the fractions 1 over 3 and minus 1,111 over 8 would be rational numbers. All integers are rational numbers. The irrational numbers, on the other hand, do not include any of the number sets we've just discussed. It is a number that cannot be written as a ratio, and in decimal form it never ends or repeats. The real number system consists of all the numbers, both rational numbers and irrational, which are real and not imaginary. Every real number has a unique point on the number line, so every point on the number line must represent a unique real number. The real numbers form a very dense set of numbers. Between any 2 points on the number line lie an infinite number of rational numbers and an infinite number of irrational numbers. In other words, though it may be hard to imagine, you will always find another real number between any two real numbers. A rational number is a real number that can be written as a fraction, i.e. as a ratio. For example, 1.5 is a rational number because 1.5 as a fraction is 3 over 2. The formal definition is, a rational number is a number that can be written in the form p over q, where p and q are integers and q does not equal 0. So a number like 8 is a rational number because it can be shown as 8 over 1. 0.25 is equal to the fraction 1/4, so it would also be a rational number. Even a recurring decimal like 0.16 recurring is a rational number because it can be written as a ratio of two integers, 1/6. More numbers than you can imagine can be formed this way. The fraction 22 over 7 is often used to represent pi, which is irrational. Is 22 over 7 a rational or irrational number? 22 over 7 is a rational number because it is the ratio of two integers. It is a rational approximation of pi, but isn't exactly accurate. The reason being that irrational numbers can't be written as a ratio or fraction, and their exact values can't be written in decimal form because they'd never end or repeat. Mathematicians have calculated the square root of 2 to more than 2 trillion decimal places, and there is no pattern of repetition. However, we can show irrational numbers on diagrams or on the number line. If we draw an isosceles right-angled triangle with two sides equal to 1 unit, the length of the hypotenuse will be equal to the square root of 2, according to the theorem of Pythagoras. So, the number can't be represented as a fraction, and it can't be represented accurately as a decimal. But it does have a very real representation geometrically and as a position on the number line. The hypotenuse method can be used to show the roots of whole numbers from the square root of 2 and upwards. If we draw another right-angled triangle with a side of 1 unit on the hypotenuse of our constructed square root of 2, then the new hypotenuse would be equal to the square root of 3, and we can carry on in this way. This is called a Pythagorean spiral. The square root of any whole number that is not a perfect square is an irrational number, so many of these lengths are irrational. The exceptions, of course, are the roots of perfect squares such as 4, 9, and 16. The theorem of Pythagoras can be used to represent irrational numbers on the number line. For example, to represent the square root of 5 on the number line, 5 is equal to 1 plus 4. So if root 5 is our hypotenuse, we can use the square root of 1, which is 1, as one side, and the square root of 4, 2, as the other side. Then measure and construct a right-angled triangle with a side of 1 unit vertically from 2, and join OA for a hypotenuse equal to the square root of 5. Now set the compass width to the length of OA and use it as the radius. And draw an arc on the number line. This gives the position of the square root of 5. It is slightly bigger than 2 and confirms an important property, that every real number has a unique position on the number line. If we add, subtract, multiply, or divide, except by 0, any two rational numbers, the result is always a rational number. They are said to be closed with respect to addition, subtraction, multiplication, and division. What about operations on irrational numbers or combinations of irrational and rational numbers? The sum and difference and quotients and products of irrational numbers can be rational or irrational. The sum of two irrational numbers, for example, the square root of 5 plus the square root of 3, is irrational. If the irrational parts of the numbers have a zero sum, i.e., they cancel each other out, as they do here, then it is obviously rational. And if we take an irrational number like 4 plus the square root of 2 plus pi and subtract another irrational number, root 2 plus pi, then we get 4, which is rational. So, we conclude by saying that the set of irrational numbers is not closed for addition and subtraction. Similarly, it is possible for some irrational numbers to multiply to form a rational product or divide to form a rational quotient. For example, the square root of 5 multiplied by the square root of 3 is equal to the square root of 15, which is irrational. Or, as the quotient of 2 root 2 divided by root 2 is equal to a half, because the root 2's cancel out, the answer is rational. So we also conclude that the quotients and products of irrational numbers are not always irrational. What happens when we find the sum of a rational number and an irrational number? The sum of 5/3 and root 3 is an irrational quantity. So can we conclude that the sum of a rational number and an irrational number is always irrational? Let's assume the opposite. That the sum of a rational and an irrational number is also rational. We can write our rational number as a ratio of two integers, a and b, and add an irrational number, x. Then according to our assumption, the answer is also rational, so we can write this as a ratio of integers m and n. We manipulate this equation by subtracting a over b on both sides and get x equals m over n minus a over b. Then simplify the fraction on the right-hand side by writing it as one fraction with the same denominator, nb. But we have now formed a fraction that has an expression that will be an integer in the numerator and an expression that will be an integer in the denominator, which means x cannot be an irrational number after all. It can be written as the ratio of two integers, which is the definition of a rational number. So we've contradicted our original assumptions and can conclude the sum of a rational number and an irrational number is always irrational. We've used a proof by contradiction to show this result. We can work in exactly the same way to prove that the difference of a rational number and an irrational number is also always irrational. Let's see what happens when we find the product of a rational number and an irrational number. The square root of 5 times 2 is equal to 2 root 5, an irrational quantity. So can we conclude that the product of a rational number and an irrational number is always irrational? Let's assume the opposite, that a rational number, which we express as a fraction a over b, multiplied by an irrational number x, gives a rational answer, which we represent as m over n. We manipulate this equation by multiplying b over a on both sides and get x equals m over n times b over a, which gives us the fraction mb over na on the right-hand side. But we have now formed a fraction that has an expression that will be an integer in the numerator and an expression that will be an integer in the denominator. This means that x cannot be an irrational number after all, and we've contradicted our original assumptions. So we can conclude that the product of a rational number and an irrational number is always irrational. And we've used a proof by contradiction to show this result. Note that we could work in exactly the same way to prove that the quotient of a rational number and an irrational number is also always irrational. Let's consider the operation of taking the square root of a real number. We know that the square root of a negative number gives an imaginary number. However, there is a theorem that states that any non-negative real number has a square root which is also real. Or, for any real number x greater than 0, the square root of x is real. We'll show this geometrically by constructing the square root of 4.35. First, construct a line with the length of 4.35 and then extend it by 1 unit. Label it ABC. Let AC be the diameter of a circle. Now draw DB perpendicular to AC. The length of DB is equal to the square root of 4.35. And to show the square root of 4.35 on the number line, position the drawing so that B is at 0 on the number line. Use the compass to measure the length of BD. Keep the point of the compass at 0 and cut off the length of the square root of 4.35 on the number line, so we can find the position of the square root of any positive real number on the number line. Sometimes you will get a solution that is a fraction containing a root in its denominator. You should never leave an answer with a root in the denominator. We follow a process called rationalizing the denominator to write the fraction in a different form. Simply multiply the numerator and the denominator by the same number, which will remove the root from the denominator. For example, multiply 2 over 5 root 3 by root 3 over root 3. The new numerator is 2 root 3, and the new denominator is 15. When the denominator is not a monomial, there is a different process to follow. For example, 2 over 2 minus root 2. In these cases, we need to use two identities based on algebraic identities. Here they are. So in our example, we know we need to multiply by 2 plus root 2. We can use the identity to get the denominator in one step, but let's work through it to show why we get this result. The numerator will simply be 2 times 2 plus root 2 in brackets. Then the denominator is the product of the two brackets. 4 plus 2 root 2 minus 2 root 2 minus 2. The denominator simplifies to 4 minus 2, which is 2. Then the 2 in the numerator and the denominator cancels to get our final answer of 2 plus root 2. Let's go over an example to apply the second identity. How would we rationalize the denominator in 3 over root 5 minus root 7? We'd need to multiply the numerator and the denominator by root 5 plus root 7. We can use the identity to get the denominator in one step, but let's work through it to show why we get this result. The numerator will simply be 3 times root 5 plus root 7 in brackets. Then the denominator is the product of the two brackets. 5 plus root 5, root 7, minus root 5, root 7, minus 7. The denominator simplifies to 5 minus 7, which is negative 2. The final answer is negative 3 over 2 times root 5 plus root 7. There you go. Now you know how to write a fraction so that the denominator is in rational form.